So this actually starts off with something that we talked about yesterday, which is, you'll recognize actually this pretty much. This stuff here, I think I just copied and pasted some of the notes from yesterday. But what I'd like you to focus on is what this says right there. It says we can use both y equals a times b to the x, which is the form that we used a lot yesterday, right? We did a lot of generic graphing and stuff. But what we're going to focus on more today is this more specific form, y equals a, and then there's a parenthesis to the t. I just want to show you that it's the same format. It's y equals some value a times something to a variable. In this case, it's t. I changed it from an x to a t just because a lot of the applications that we use involve time. You could also just put an x up there as your exponent as well. But here's what this base is going to be. Instead of using b, what we're going to use instead is 1 plus or minus r. It's either going to be 1 plus r or 1 minus r. It's going to be one of the two. All right. If it's 1 plus r, that means whatever the rate is, we add to 1, so it'll be over 1. That makes it growth. If it's 1 minus r, it just means it's going to be a number that's less than 1, which makes it decay. And that's what all this stuff kind of says right there. So take a second to get that stuff down. I don't think really anything down there is new, though, right? That's basically a review from yesterday? Okay. So take a second to write that down if you haven't. And then what we're going to do is try these problems down here. I've got a few of them done already, these two guys right here, just for us to kind of use as examples. So take a second, kind of don't just copy it down. Read what you're copying down so as you do, you understand why it makes sense that that's there. For example, we said yesterday the A value is your initial amount. That's why the initial amount is 3. The growth factor is 1.62. That's the base. That's the base of the power. Okay. Oh, by the way, why is this growth? Because b is greater than 1, right? That's greater than 1, so that's why it's growth. All right. And then the growth rate is the difference between your base and 100%. So your growth rate here is 62%. Okay. So that's why in the next one, we don't put 36% right there. It's the difference between what your base is and 100%, which in this case would be 64%. Obviously, it's 64% less, but that's why this is decay. All right, take a second to fill that guy out if you haven't yet. Spencer, what do you got for your first blank there? Is this exponential growth or decay? You gotta talk louder, man. The microphone's gonna pick this stuff up.
Decay.
That a boy. I'm only calling on you because when I asked if we should record today, you said no. So you kind of made your own bet. All right, what's the initial amount?
14.
14 because of that guy right there. What is since we called it decay, these are both decay right here. Okay. What is the decay factor?
0.95.
Good. And what is the decay rate?
0.05%.
Good. Questions? Spencer rocked it. Nice job, Spencer. All right, so now what I'd like you to do is try the 3 that are below this. I'm going to give you about a minute and a half. Fill those out. We'll see what we got. All right, let's check these out here. Oh, that didn't work. Supposed to cover the answers up. All right, so here's what we got for the first one here. I needed something to cover the answers up, even though it's not covering the answers up. I love this software. It's great. It's good software. Okay, so the first one, what do you think? Good? Decay. Initial amount is 100. We got a growth factor of 0.12, decay factor of 0.12, decay rate of 88%. I'm going to skip over to JP here. Still one of my favorite pictures of all time. That's because this was a trigonometry test. That one's in radians and that one's in degrees. Yeah. Fancy, lazy, whatever you're going to call it. All right, so we have, I think that's pretty straightforward, right? That's an example of kind of a half-life situation, right? and something is half of what it was before, whatever the time amount is. All right, so the middle one here, this is kind of a goofy one because of the 5. This one is a little goofy because of the 5 right there, but that 5 is still used to find out your percentage. So the growth factor is 5. But since it differs from 1 by 4, the growth rate is 400% then. Okay, or just you could say 4. All right. Does that make sense? Because in order to find the growth rate, you always take B and either subtract it from 1 or subtract 1 from it. So 5 minus 1 is 4. That's how 5 minus 1 is 4. It's kind of weird because if I told you something was doubling, what is the percent growth then? It's 100%, right? If something's doubling, it is getting exactly that same amount every time. Whatever the time is, I don't know. But that's why you have 2 as a base, because the difference between 2 and 1 is 1, so it's a growth rate of 100%. All right, let's take a look at some of these exponential models on here. This is a great section in terms of applying some of the things that we're doing to real-life applications today and tomorrow. So we're going to start with something that depreciates in value pretty quickly, and that's technology. I think we have another one that has to do with cars, too. It says a computer is valued at $6,500, and it depreciates at the rate of 14.3% per year. That is one heck of a computer, by the way. Write a function that models the value of the computer after T years. Graph the function on your calculator. All right, here we go. V equals, and then I just got blank, and then a parentheses taken to T. So what goes here? Y. It's the initial amount, right? If we were to graph this thing, if we were to graph the situation, which we often will, actually, I think we will graph this one a little bit. So if you have a graph calculator handy, pull that out. All right, we'll get to graphing in a second here. So since it grows at 14, oh, I'm sorry, it depreciates, right, at 14.3% per year. Subtract that from 1, right? So you get what, 85.7? Okay, 85.7, right? Don't put 1 minus 0.143 in here. Actually put the 0.857. We don't want 1 minus in there, okay? I mean, you can write it as a first step, but why? So there's our model. That is the model that we're going to use. Now, this next question, question B, says find the value of the computer after 3 years. There really is no need to graph it for that question, right? It's the next question. When would the computer be worth $5,200 that's going to require a graph? Okay, so what we're going to do is put this into a graph calculator right away. Don't worry, this is not going to take as long as what some of our other graphs. What was the last stuff we graphed? I don't even remember. Maybe square roots, cube roots. Those weren't bad. All right, so we're gonna put this into our equation editor. All right. If you got a question, if I go too fast or something, let me know. But we're all here, hopefully, right? Little reminder: make sure that up here, none of those plot 1, plot 2, plot 3, those should not be highlighted. If they're highlighted, go up and hit enter and unhighlight it. Okay. Otherwise, it's not gonna be able to graph anything. All right, so into our equation editor, first equation, we're going to put our model. So 6,500. Uh-oh, that's not working. So 6,500. And then in parentheses, 0.857. No, hold on, before we go too far. We're going to answer a couple questions here. Don't put a 3 as your exponent. Put an x as your exponent. So take it to the x. All right, don't put a 3 in there. You're just going to get a straight line when you graph it. What's up? All right. Anybody else have a starfish as their background on their calculator? Okay. I've never seen that background before. I get the whole, there's like a bubbler, like a fountain thing, right? Because then you do a parabola. I have no idea why a starfish should be on there. Okay. So here's what we want to do. You have to think about what I like to call the applicable domain and range in order to figure out what your window is. Okay, hit window. All right. Think about what x represents in this problem. X is the exponent, obviously, right? In our problem, we called it t, right, on paper. T is time. So what would be some good values here? What would be a good starting value? What do you think you should have as the initial starting value? How do we get 6,500 as our initial value? Because you have 0 as t, right? In order to get this as your initial value, that's because t is 0. If t is 0, 0.857 to 0 is 1, right? That's where you get the 6,500 from. So t being 0 gives us that starting amount. So let's make 0 our first x value, our x min. Now, if you really want to see the y-axis, you could actually make it like -1 or something, but we're okay. So the x maximum, we have no idea how long we're going to own this computer for, right? How about we leave it at 10? We'll just say 10 years. It's $6,500. Hopefully it lasts 10 years. I don't know. We'll see. We at least need to see 3, right, to answer part B. So I think let's leave it at 10. We might have to change that. Okay, so we got that. Leave our scale at 1. Okay, y minimum. Y is the actual value of the computer. What do we know this thing is never going to go below? 0, right? It's an exponential decay function. It has a horizontal asymptote at 0. So we can make that 0. For the y max, what do we at least want to show? I would say the 6,500, right? If you want to go a little bit bigger so that you can see it, I don't know. I'm going to go 6,600. And instead of going y scale of 1, just because it would make the y-axis look real chunky, I'm going to go by like hundreds. Question? Questions? Good? Raise your hand. Yes?
I don't know if this matters, but the two numbers in the bottom, like on the very bottom of the screen.
Yeah?
Does that matter?
No. Nope. Are we ready? Go ahead and hit graph. Oh, that was fast. I don't know what's going on. Mine is like supercharged right now. Mine never graphs that fast. Okay, does everyone's look somewhat like that? Actually, if we all put the same window in, they should look pretty much identical. Okay? You okay? All right. You look like you're taking a selfie with your TI-84. All right, so now to answer question B, understand we could just quit out of this graph, right? And go and take 0.857 to the third, multiply it by 6,500, right? It's an easy way to calculate that, but as long as we have the graph, why don't we do this? Everybody hit trace, and this is a shortcut. To find the value of something for a certain x value, if you hit trace and then immediately type a number, like 3, and it says, oh, you want x to equal 3, hit enter, and it'll tell you the exact value. You should have 4,091.25. This is monetary value, so let's round it to the 100. Let's get used to rounding all of our money answers to the 100th. All right? Yes?
Sorry, can you repeat how you got to the volume?
Yep. So let me hit graph so it's not there anymore. Just hit trace. If you ever miss what I hit, it's always red on the calculator. So you hit trace and then just immediately hit 3. Actually, it doesn't have to be immediate. It just has to be the next button that you hit. There's not like a timetable on it. Okay, and then hit enter and we're good. Is everybody okay at that? Anybody have a different way that we could have solved that? Yeah.
Well, besides the second and then the graph of the second.
Perfect. Look at number 3. And then if you see how it says 4091.2, if you want to see the whole thing, go over on it and then look down below, you've got the whole thing. So there's a table as well. Very useful for that. Okay, good? All right, so now they ask us this question. When would the value of the computer be worth 5,200? So now we want to find out when y will equal 5,200. So what we could do you see the table that I'm on? I'm actually glad that Abby brought up the table because look we can kind of guess that it would be 5,200 between year 1 and year 2, right? But that's just a guess. So let's go back to y equals and put in a second function. Y equals 5,200. Let's find the intersection of those two graphs. Wow. Man, I don't know what's going on with this thing today. Okay, so do you remember how to do the intersection? If not, watch. Here we go. Ready? We're going to find the intersection between those two lines. So we go second, trace. That takes you up to this calculate menu on the graph, like calculate different things on the graph. All right, we want to calculate an intersection, so number 5. Now this is one where it asks you first curve, second curve, and can you make a guess? If you've got one of the newer calculators, it makes it easy and it color codes everything. Look at all the numbers on the screen are blue. It's basically saying, is this blue curve the right first curve? Yes, it is. Hit enter. Then it's saying, is this red curve the other curve you want to find the intersection of? Yes, it is. Hit enter. And then it says, go ahead and make a guess as where it is. I'll just get a little bit closer. I don't think that's really going to make a difference. Okay, if it intersected more than once, you definitely want to get closer to the intersection you were looking for and hit enter. And there it is. About 1.44 years, and we could turn that into months and everything, but about 1.4, actually 1.45 years after purchase. So, the natural gas problem. Go ahead and this is on the back side if you haven't seen it yet. Go ahead and just read through that little synopsis. It's pretty simple. It's a one-sentence statement about how much natural gas the U.S. consumed between 1940 and 1970, in case you ever wondered. So what always amazes me when we do this chapter is how much I think you guys don't even realize that you know you can pull from a function. So if you look at that function right there, how many, what was the initial amount of natural gas use? How many trillion cubic feet? 2.9 million, trillion cubic feet because of the A value, right? What year was that? What would T have equaled at that point in time then? 0. So let's go up here. Let's put this right up here. We're saying T should be from 0 to what then for this function? 30. That's really super duper important. Okay? T is not like 40 to 70 or 1940 to 1970. T is 0 to 30. Okay, we will almost always make our starting value 0. All right, so let's go back here. I already got the growth factor, 1.07. You guys were flying through that before. The annual percent increase is 7%. Is everybody okay at that? Okay, so now let's talk about the applicable domain and range. The values, okay, because if I just gave you this function, ladies and gentlemen, and didn't tell you anything about natural gas or the years or anything, and said, well, what's the domain and range of that function? Like the functions we were doing yesterday. The domain would be all real numbers, right? Yeah, you can put anything in for that. But the applicable domain and range for this problem is 0 to 30. And because of what we said before. How about the applicable range? Now we have that 2.91. Is that the smallest value that'll come out or the largest value? Why is it the smallest? It's when it's 0, right? And it's exponential growth. Okay, and are we all in agreement that that actually means 2.91 trillion? I'm not going to actually make you write all the zeros or do scientific notation, okay? Or you don't even need to write in trillions. It is. Okay, we're good. Okay, so how do we find that guy? Plug in 30 for t into the function, okay? So since, doesn't this ask us to graph it? No. So let's plug in 30 into that function. Oops. So I'm going to go, what's that? Oh, it does say to graph it. So let's do this. Let's go to the graph and graph it right away then. So it was 2.91 times 1.07 to the x. And then make sure you get rid of that second equation at 5,200. Okay. Now hold on. If you hit graph right now, your window is still thinking about goofy computer you bought years ago, right? So you need to change your window. So time, I got 0 to 10. What should that be? 0 to 30, we said, right? At least 30. You know, if we kind of want to see past that, we could. I'm going to go by 5s for time. Actually, yeah, I'm going to go by 5s. You could go by 1s. It doesn't matter. For the y minimum, I have 0 to, now we have no idea what this should be, right? That's actually kind of what we're looking for. So I don't know. I'm going to put in 100. I have no idea. No clue. And I'm going to go by just fives right now. This might be way off, and I'm okay with that because I want you guys to see that, like, that's how you learn how to find the window and stuff. You have to, like, fail as you do it. Yes. Yes. Okay, so we have, let's hit graph and see what this thing looks like right now. Well, it's a start, right? I mean, I don't think that's great. I'd like to see a little bit more of where it goes up. Let me see what else they're asking us here. Estimate the natural gas consumption in 1955. Okay, I'd be able to do that. Estimate when the natural gas consumption reached about 11.26. 11.26, I went up to 100, right? So 11.26, maybe 100 was a little much. Let's scale back a little bit on that Y max. I'm going to go to like 50 instead. Okay, and that might actually be too much. We'll see. But let's do this. Let's find the value when x is 100 or 30, right? How do we do that? How do you find the value when x is 30? Trace and then 30. So 22.15. That is. So now that we know that, we know we don't know. We know that we don't need to go much bigger than that, 22.15. So I'm going to go back to my window, and I'm going to even go down to 25. That looks a little bit nicer. Okay, so now we can answer everything that we want to answer. It says, estimate the natural gas consumption in 1955, right? So we do basically the same thing we just did. We go trace. What number should I be putting in? 15, relating t equal 15, trace 15, and we get 8.03 trillion cubic feet. If I'm going too fast, please let me know. Don't worry about the fact that this is being recorded. I can pause it. All right? Okay, so how do we do the next part? Walk us through it. What do we do? Go to the y equals, and then we want to put in a second function, right? Yeah, 11.26. Graph that again. How fast this is graphing right now just amazes me. I don't know what's going on. Usually this thing is so slow. So we're gonna go. Okay, how do we do the intersection again? Oh, this is like a thing of beauty. I'm glad I got that on camera. And then number 5, intersect. First curve, sure. Second curve, yeah, looks good. Guess, actually, I think where we're at is close enough, but. So we got almost 20 years. You know, what I would do, like if this were a quiz or test and I were you, first of all, actually, this is a great thing to throw out there. Let's say you use a graphic calculator to answer this question on the test, okay? If you're going to use a graphic calculator, you better sketch a little graph. And I'm not talking anything crazy. So there's my exponential function. All I'm doing is showing, hey, here's how I graph this thing, or here's how I solve it. So that's the line 11.26, right? I don't know why I put it way over there. And obviously the blue function is the exponential function. But by showing this little sketch here, what I'm saying is this is what I found as my x value. Okay, that x value, I'll just call it x sub 1, and then I'll just say here x sub 1 is 19.99. I'm going to go out a few decimal places here. But then to answer the actual question, let's just say about 20 years, right? Oh, yeah, it does. But I like putting this on paper, too, to show, hey, here's like exactly what my calculator gave me. And then to say, in about 20 years, but let's be specific here. We're told that year 0 is 1940, right? Or just before 1960. Like literally, this would be 1960. December of 1959. Cale, did you work out the day yet in December of 1959 that would be? Okay, we'll come back to you, okay? All right. I'm kidding, Cale. I'm kidding. Are we okay with this? All right. We're going to end here with a little bit of financial sort of problems here. We've got compound annual interest, or I should say, interest that is compounded annually. Compounded means basically it's calculated and put into your account. Okay? So if something is compounded annually, that means you got your money in this account all year long, and then once a year, whenever it is, you get a statement saying, hey, thanks for banking with us. Here is the interest you earned, and we'll see you next year. Okay, and whether you take money in or out, that obviously things change. But if it's compounded annually, once per year, that interest is compounded. A lot of times, interest is compounded multiple times per year, daily, monthly, quarterly. Okay, so in that case, actually, let me back up for a second. In the first case, we'd just be using that. If it's annual, it's that. By the way, if you look at that thing, is that any different than the models that we've been using so far? Just different letters, right? Instead of A for the initial amount, we have P for principal. Okay? Instead of Y, we're going to call it A for like the amount in the account, right? And then we have our R and our T. It's the same thing we've been using. If it is compounded some other time per year, N times per year, we use this bottom formula. So in other words, what we need to do is take that rate and divide it out. So if it's compounded monthly, we need to take that rate and divide it by 12 to kind of like spread the rate out, right? But by the end of however many years, you've compounded it, not the number of years, but N times the number of years, which is why you have to multiply your exponent by N. So for example, if it was compounded monthly, right? After 5 years, how many times has it really been compounded? 60 times. So that's why you have to take it to the 60th then up there. All right, so let's try one of these here. This says you deposit $1,200 into an account at 3.8% interest compounded quarterly. So quarterly means that N equals what? How many times a year is it compounded if it's compounded quarterly? 4. So N is going to equal 4. If it were monthly, it'd be 12. Daily, it would be what? 365. Okay, numbers that you should know. All right. So let's write a little model here. So we've got 1,200 as our initial amount. Here's what I like. Write exactly how I'm writing this, please. We're going to go first like this. 1 plus, what's the rate? 3.8%, right? As a decimal, that would be 0.038. Since we are dividing by N, we want to divide by 4. And then up here, we want 4 to the T. Does that all make sense so far? Okay, the first thing I'd like you to do is figure out what that is right there. Just the stuff inside the parentheses. So in other words, I'm going to do it right here too. We're going to take 0.038 divided by 4, and we get 0.0095, and I'm going to add 1, and I know that adding 1 just puts a 1 in front of that decimal, but I want that number in my calculator. That's why I use my calculator. So here's what this just turned into. 1,200 times 1.0095 to the T. Do you notice how, oh, wait, the 4 is still there, isn't it? The 4 is still there. I'm getting excited here because I know that we're running out of time. Okay? The next thing I'd like you to do, I'd like you to do one more thing. I'd like you to take 1.0095 to the 4th. So it's on your calculator. Just hit the caret key into the 4th, and you get 1.0. So we have 1,200 here. Then we have 1.03. I'm going to go 9. I'm going to round it to the 1,000th. However, this is one of the most important things I'm going to say to you today. Even though you round it on paper, you have to use the number that's on your calculator in your calculations. All right? So do you notice how now the 4 is gone, right? Because we took it to the 4th. We don't need that 4 anymore. Guys, what we just learned is that compounding something at 3.8% quarterly is the same as compounding at 3.9% annually. So in other words, the more you compound it, the better the percentage. Now, is there much difference between 3.8 and 3.9? Not a whole lot. Well, if you're talking about big amounts of money, there kind of is. But, all right, we're going to have to end there. All right, sorry for that. Class just ended, but I'm going to finish this video up here as long as we're this far so we can complete these examples. So what we've done here is come up with a function that actually models what the annual growth rate would be of this particular account with the 3.8% interest compounded quarterly. So, I mean, you really could get your answer, and I would be okay with this as an answer too, really with the 4 as the exponent. But actually, I shouldn't say that. Let's try to get our answer simplified down to this form right here. All right, where we have the 1.039 as our base, and I rounded it to the thousands. You could round it a little bit differently. I would go at least to the thousands here though, because then you can see the difference between the original interest rate and what this one is here. So, having said that, that is our final answer here. What we're going to do now, or that's our final model, what we're going to do now is find the value of the account after 5 years. So what I'm going to do is store this value on my calculator. Actually, no, I'm sorry, I don't need to do that. I thought we had to graph this thing. I'm just going to put 5 in for t, but watch how I do that. So we're going to find the amount when I put in 5. So I'm just going to put in, what did I round to? I rounded to this. So I'm going to write my same rounded value, but this is a really, really important part right here. Don't use this exact equation. Use the number that's on your calculator. Okay, so what I'm going to do is go right back to my calculator and immediately take this value to the 5th and then multiply that by 1200. So our answer is $1,449, and if we round to the 100th, 80 cents. We don't want to use this because it could give us a little bit different answer depending on what we round it to. Use the number on your calculator. Make sure you make a note of that to yourself. We round when we write, but then leave the exact value on your calculator and use that to do all your other calculations. Okay, so the next problem says we're going to deposit $1,200 into an account that's compounded monthly. So this time our end value is going to be 12. So because it's monthly, n is 12, and I'm just going to put a 12 right there and a 12 right there. Our rate is 0.045. And they want us to write a function that models that. So I'm going to go through that same process that I did before. I'm going to take that 0.045. Let's clear out here. 0.045 and divide it by 12. Add that to 1. Okay, so we have this right now. I'm just going to take a second to write that down. That equals 1200 times 2. Oh, I accidentally did 1 twice, didn't I? So let me subtract 1 here. I want to keep that value on my calculator. 1200 times 1.00375, and that is taken to, that 12 is still there, the 12t. And now what I'm going to do is I'm going to evaluate this right here. So I'm going to take that to the 12th. At 1.0459 or 1.046. 1.046, and now I don't need that 12 anymore because I evaluated with it already. We have 1200 right there. So there is our final model right there. Find the model after 5 years. Okay, so now we have another chance to use that number on our calculator. We're going to take that to the 5th. I just used function notation right there, a of 5, basically saying the amount after 5 years. So we're going to take that to the 5th and then multiply it by 1200. Make sure you hit enter after you take it to the 5th. Oh, jeez. Man, I'm having some issues here. All right, so we've got this. I'm going to take that to the 5th. It keeps double hitting on my calculator. Oh, okay. Sorry, folks. try this one more time. So we're going to take that to the 12th. Nope, that's not what I want to take to the 12th. Okay, there we have it. Take that to the 5th. Please don't hit it twice this time. There we go. We're going to multiply that by the 1200. So we're at 1502.15 dollars. All right, a little bit of a change up in this last example here. It says if you wanted to have $10,000 after 10 years in an account compounded quarterly, how much you're going to have to invest. So really, we're looking for P here, where it says how much would you have to invest. We're looking for P. We know the amount we're going to have at the end. Okay, so we want to find the principal that we have to put in. I forgot to put a rate here, so we're just going to use that same 4.5% like we did in the last problem. All right, so we know that A equals, I'm just going to rewrite that formula again real quick. The principal times 1 plus r to the n taken to the nt. So if we want to solve for p, if we want to get p by itself, we'd have to divide by that whole power right there. So p would be equal to a divided by that 1 plus r divided by n to the nt. So I'm just going to use that to find out what P should be when the amount that we know we want to have at the end of 10 years is 10,000. So that's our numerator. And we're going to divide that by 1 plus, let's see, our rate is 0.045 divided by n. We are compounding quarterly here, so n is going to be 4. And now in this one, we're not leaving a variable up on top in this one. It doesn't ask us to write a model or anything. So we can take 4 times t right away. T is 10. So this is going to be 40. And basically, this is put this in your calculator and see what you get. If you have the ability to put in fractions, I would do that. So I'm going to go alpha y equals, and number 1, 10,000. Make sure it's not double entering anything again. And then down here we've got our 1 plus, throw in a fraction in here, why not? 0.04544. And you could calculate what this is separately too if you wanted to. Close that up. That is being taken to the 40th. Looks like we're going to need about 63, almost $6,400. So this is about 6392 point. I'm just going to put that there and then just come over here and say I'd have to invest about or at least $6,932. Oh. Write that again, try that again. $392.32. Or to be safe, 6,400. I don't know for sure I'll hit that 10,000 as long as I don't pull anything out.